Okay, so these are the notes for 8.4 here in stats, and what we're doing is we're doing a z-test, a hypothesis test for the true proportion.
Any seniors planning to attend CSI this fall need to come to the library right now. Thank you.
All right, sorry about that, but when the data is given as a percentage or a ratio of populations, you'll need to use a z-test for proportion. In order to do that, we have to use this specific formula for finding z. Now, this is if we're going to use the traditional method. This is how we would find the test parameter or test statistic, where p is the population proportion and p hat, remember, is our sample proportion, which is equal to the number of yeses out of the number in the sample size. We are not going to use this one in this class. What we're going to do is allow the calculator to do it for us. This is still one of those that we can. In 8.5, in the next section, we will have to do things by hand for the chi-squared distribution. But we can use the p-value method and even the traditional method with the z-table and just use our calculator. So an example of this, similar to what we've been doing, a dietitian claims that 60% of people are trying to avoid trans fats in their diets. She randomly selects 200 people and found that 128 were trying to avoid trans fats in their diet. And so if we wanted to set up our H0 and our H1, our null and our alternate hypothesis, we're no longer talking about the mean. We're now talking about the true population proportion. We know that the null hypothesis in this class is always going to be an equal, and since she's talking about it being 60%, that's before any samples were taken. We'll say the true proportion is 0.6. And since she's making this claim, that tells me that this is going to go ahead and be my claim. And anytime the claim is the null hypothesis, it's usually pretty safe to assume that the null or the alternate hypothesis excuse me, will be a not equal. All right. The next thing that I want to do is go and, using the p-value method, to do this, I'm going to go find the p-value from my calculator. Okay, so we'll go to our calculator, turn it on. We're going to go to stat, we'll go to tests, and we're going to run a one prop z-test. Okay, one proportion z-test. One proportion is what we're dealing with, and it is a z-hypothesis test. Our null hypothesis is that it is 0.6, so we'll start with that. The number of people that said yes was 128 out of 200, and we're doing a not equal to for our alternate hypothesis. So we calculate, and that produces a p-value of 0.248. Our z-value is 1.15. And if we were using the traditional method, that would be our test value. But here, the p-value of 0.248 is greater than the alpha at 0.05. Therefore, I do not reject H0. We need the p-value to be very small. Here it's too big, so we do not reject. And we would summarize by saying there is not enough evidence to, and because my claim is the null hypothesis, we will say to reject the claim. Okay. Next question, another example. It says, family of medical leave act, job protections, unpaid time off for work from serious illness or birth of a child. In 2000, 60% of respondents of a survey stated that they were very easy to get time off for these circumstances. Researcher wishes to see if that percentage has changed. Okay, and here's our sample data right here. So our null hypothesis has to come from something independent of the sample. Well, up here it says it was 60%. So I'm going to go ahead and say that p equals 0.6. My alternate hypothesis is something else. We want to see, has the percentage changed? Changed would just be not equal to the 0.6. And I'm going to go ahead and say that that's the claim. Again, if the question doesn't say specifically that they're claiming that it's the same, their interest is in that has it changed, those would all be things that would point us towards having that be our claim. All right, we need to find our p-value. So we go back to our calculator, and plug in. Okay, 0.6 is still that percentage, but now it says that we got 53% of the 100. Well, to figure out how many people actually said yes, I'm just going to do 0.53 times 100 right here. Now, obviously, I know that 53% of 100 is 53, but if it was of another number, 53 of 275, like I could just type in 0.53 times that, and it will evaluate and tell me how many. There was 100 people in the survey, and we're still doing not equal, so we calculate. And my p-value here is 0.153. Be careful not to confuse it with the p-hat that's right below it. What we're looking for is just the straight p-value, 0.153. That number is greater than alpha at 0.01. So again, we do not reject H naught. There is not enough evidence to, and because our claim is the alternate, we're going to say support the claim. And then we're done there. So that's really what's different. We're doing p-values instead of z-test and t-test. If you're talking about the population mean and you have the standard deviation sigma, you can run a z-test. If you do not know the population standard deviation, but you know the sample standard deviation, you can use a t-test. If your goal is to talk about the proportion, you can use the one-prop z-test. Okay? Each one has a p-value. That can be, so you can use the p-value to make your decisions. Remember, if p-value is less than equal to alpha, we reject. If p-value is greater than alpha, we do not reject. There are a few times you will come across problems where an alpha is not given. So if you don't have an alpha, that means you have to make these decisions on your own. If the p-value is ever less than 0.01, meaning 1%, we can reject the null pretty consistently because the difference is highly significant. However, if the p-value is between 0.01 and 0.05, we still, again, this is nobody's given us an alpha. If someone gave us an alpha and said it was 0.01, we follow the rule for up above, guidelines for when alpha is given. But when it's not given, if we're between 0.01 and 0.05, we can choose to reject the null because there is a significant difference. It's not highly significant, but it is significant. However, when the p-value lands between 5% and 10%, right, 0.05 and 0.10, we need to think about the consequences. Is this a problem where rejecting the null when I shouldn't reject it, that type 1 error, would lead towards life and death? Would it lead to financial ruin? What are the consequences? Is this a big deal if I reject it when I shouldn't? Or is it kind of like, you know what, it might rain today and I didn't bring an umbrella. There's not a lot of risk in a real problem. I could be wrong, but I'm not going to live with consequences that are going to cause other people to die, right? However, if p-value is ever greater than 0.1, we're going to always not reject the null hypothesis because it's just not significant enough. So that is what we do when we don't have an alpha given. If p-value is greater than 0.1, we're not rejecting anything. We need more convincing data. All right, good luck, guys, and we'll see you in class.